My name is Suresh Srinivasan. I coordinate the Beginner Special Interest Group for the Minnesota Astronomical Society. Thank you for joining us today. Really looking forward to this talk by Dave Falkner on the Great Debate. A couple of points just ahead of time, just to remind everybody, the Minnesota Astronomical Society has a YouTube channel. And so all the monthly meetings, these BSIG presentations are all posted there. And so you can find it by just going into YouTube and in the search, type in Minnesota Astronomical Society, fully spelled out, and you can subscribe to our channel. The other thing too I'm going to ask is, and I'm going to do it myself here, is everybody that's got their video open, please close it. That'll help with the bandwidth for this presentation. So Dave should be the only guy with his mug showing, his beautiful mug.
Yeah.
And then let's see, I'll just do a brief blurb for next month. The next meeting will be on January 22nd at 1 p.m. Jerry Jones is going to present Astronomical League programs for beginners, as well as some observing techniques that help him with his observing. I don't know if Jerry's on here just yet, but that's great. All right, with that, I'm going to introduce Dave Falkner. Almost everybody in our club knows Dave, ex-president of the club. One of our clubs, is it 2 or 3 NASA ambassadors? I think Ron Schmidt's the other one. Am I right, Dave?
Ron Schmidt's an ambassador, and I think Brad Nassett may be ambassador now too.
That's right. So we have 3 of them.
Yeah.
So I'm really happy that Dave agreed to do this talk. It's a really interesting topic. For me, it's one of those great topics of the 20th century that really has led all the way to today in terms of shaping the universe and how we perceive it. So with that, I'm going to go ahead and turn it over to Dave.
Okay, thank you very much, Suresh. I think I'll start out by telling just a little bit about myself. So I've, as Suresh says, I've been in astronomy for quite some time, not as a profession, but as an amateur. I became interested in astronomy when my dad took me to a planetarium show when I was a kid, and I just fell in love with astronomy. And of course, that was back in the space age, the space race too. So, you know, that kind of helped as well. When I was a teenager, I ground a 6-inch mirror, built a little telescope, 6-inch telescope. And then, you know, just kept my interest in astronomy. Eventually I joined the Navy and had a family. And so my interest kind of ebbed and flowed with that. But when I came up to Minnesota, I became interested, you know, kind of piqued my interest again and joined the Minnesota Astronomical Society, and has been heavily involved in that, as Suresh indicated. I do a lot of outreach because I enjoy sharing my knowledge of astronomy with others, and that's what got me into the NASA Solar System Ambassador Program, which is a program where volunteers for NASA and the Jet Propulsion Laboratory go and speak to the public about space exploration, and NASA missions in particular. So today, we're going to talk about the Great Debate of 1920. It's hard to believe, but this is just a little over 100 years ago. And at that time, we had a much different view of what the universe was. And this debate dealt with the controversy among astronomers at the time about the size of the universe and the nature of what they called spiral nebula, which we'll talk about. And during the debate, other observations were brought up that altered what astronomers and other scientists believed about the size and the center of the Milky Way, and quite frankly, humanity's place in the universe. And changing that role of humanity really was a big deal. And I'll explain why as we go along. But to understand the significance of some of their arguments, we needed a little bit of a background here. So I'm going to go into the background, then we'll move into the debate.
Hey, Dave, real quick, before you do that, one thing I forgot to mention is if you have a question for Dave, drop it into the chat feature on Zoom. And then every minute or every couple minutes, I'll stop and ask Dave myself. That'll allow Dave to keep the flow going and keep his rhythm. Thank you.
Sounds good. Sounds good. Okay, so when you go outside at night, especially in a really, really dark sky night, you see a lot of stars out there, right? So, and there are, you know, thousands of stars that you can see in the night sky. But now imagine yourself that you've gone out there looking at the sky, looking at the night sky, and you don't know anything about the universe like we know today. and there are no large telescopes or computers or anything like that. You just know what you see, basically. And what it appears is that everything is kind of moving around us. We're not moving, the sky is moving, right? Everything moves from east to west around us. Okay. Now, when you look at the night sky, all the stars you see are in the Milky Way. In fact, there's only 3 objects that we can see with the naked eye that are not in the Milky Way. Okay. And those objects are the Andromeda Nebula on the left here, and then the large and small Magellanic Clouds. Everything else is in the Milky Way galaxy. And so at that time, way back when, this is how they looked at it, that the sky, the celestial objects, and the sun and the moon, they all revolved around the Earth. So the first person who really wanted to define what the universe was back in the 1st century AD, a guy named Claudius Ptolemaeus, also known as Ptolemy. Okay, and Ptolemy went out and he observed this. He observed that the sun and the moon and the planets and all the stars seemed to revolve around the Earth. And so he defined the universe as the Earth was in the center and everything revolved around the Earth. And he studied the sun, the moon, and the planets, and came to the conclusion that this is what it looked like. You had the Earth at the center, with everything revolving around the Earth. And here we have the moon first, and then Mercury and Venus, and then the sun, and then Mars, Jupiter, and then Saturn. And then beyond that was the whole celestial sphere of stars that didn't seem to move with respect to each other. It was like they were attached to this huge celestial sphere. Okay. Now, he figured that the moon and the sun and the planets must be on crystal spheres, because we can obviously see through those to the celestial sphere. And so, and the celestial sphere completely surrounded the Earth. Didn't know how far away it was, but it was a long ways away. And so this is what he defined the universe as: Earth at the center, with everything revolving around the Earth. Okay. So this is the way that we saw the universe for some 1,500 years. Okay, the Earth at the center, everything revolved around it. Stars were points of light on a celestial sphere. The planets were wandering stars. The planets, sun, and moon were attached to crystal spheres. Meteors were atmospheric events, like lightning. And they had no idea what comets were. And whenever a comet appeared, it was always a bad omen. One of the reasons why there were a few people who challenged this a little bit, but they really weren't taken very seriously, and their ideas were not widely published, mainly because this was also the view that the Roman Catholic Church had as well. And you have to understand that through these 1,500 years, the Roman Catholic Church was not only a religious leader, but also it was heavily politics, and was also the scientific authority at the time. And they saw in the Bible, in Genesis, where God made the heavens and the earth and placed the humans, the mankind, if you would, in charge of the firmament and everything that was made. And so this whole idea of a geocentric universe made a lot of sense to them, and they didn't like anybody challenging that. And anybody who challenged that view was considered a heretic and was brought before the Roman Inquisition. And so there wasn't a whole lot of incentive to challenge this view of the universe. But I think it's important to see that for 1,500 years, this is how we saw the universe. And change is hard, right? So, but the first, so there was one problem with this view of the universe, and that was that while everything appeared to move from east to west on a daily basis, if you studied the movement of the sun, the moon, the planets, they also had a movement against the background of stars that was generally from west to east. Okay, except there were times when the planets would stop, move from east to west for a period of time against the backdrop of stars, and this would be over a period of weeks and months. Okay, would move against from east to west against the background of stars, and then resume their normal west to east movement. And this was hard to explain. Okay, if they were on crystal spheres, why were they going backwards, right? So what they added to our little model there is what they called the epicycle. Okay, and that the planet on the crystal sphere was also moving in a circular fashion. And so at some point, when it was moving in a circular fashion, it would move from east to west, but then when it got to the other part of the cycle, it would resume its west to east movement. And so they tried to explain, that unusual movement of the planets that way, and created this model that tried to predict where planets would be with all of this, and they come up with a very, very complicated model of planetary movement with the Earth in the center. As you can see, it looks like a spirograph, but it's, and it was very, very complicated, very difficult, and quite frankly, it wasn't as accurate as they would like. Okay, so we now move to around the year of around 1520 or so, and Nicholas Copernicus was the first person to really challenge this, but he didn't publish anything because, again, he didn't want to go before the Roman Inquisition. But he came up with the idea that, there's a better way of modeling this that makes things much simpler. And he came up with the idea of placing the sun at the center with the Earth as another planet and having the planets orbiting the sun. And he kind of spread this word around some of his friends and colleagues and the like without actually publishing anything specifically. And it kind of started getting the idea that, this might work. Okay, so his idea and it was that the sun was at the center and that all the planets revolved around the sun, and the moon still revolved around the Earth, but this is the way that he saw things. And as you look at the planets, you can see that the planets move against the backdrop of stars at different rates, at different speeds, if you would. And so he could see where the different speeds of the planets would mean that as a planet passed another one, you could see this retrograde motion. I'll show it to you in just a minute. So, but again, he didn't publish this right away. In his model, though, when you get to retrograde motion, what would happen? Here's the example with Earth and Mars. As Earth catches up to Mars and passes Mars in its orbit, the apparent motion of Mars against the background of stars would be as it shows to the right here, where A is the first observation, then B, and then you can see where it appears to stop and move in the opposite direction, toward the west, and C, D, and E, and then at E it stops again, and then continues in its normal easterly movement for F and G. So this was a much, much simpler model of the solar system universe, if you would, and it was something that was well accepted by many of the scientists at the time, not all, but most. Again, change is hard. He eventually did publish this I'm going to back up a little bit here. In 1543, he published De Revolutionibus Orbium Celestium on the revolutions of the celestial spheres. And unfortunately, he died that same year. But since he published that and then died shortly thereafter, Rome couldn't really do anything about reprimanding him for it. And so this document kind of got out and people started reading about it. And there were a number of people who thought that this seemed like a much better way to model the solar system. Okay. And one of those folks who did believe in this was Galileo Galilei. Okay. Now, we know that Galileo Galilei was one of the first people to use a telescope to view the heavens. Now, a telescope had been invented a number of years before that, but it was used primarily for terrestrial things, for commanders to scout out armies, that were far away to, check their numbers and disposition, or for sailors to check out ships at sea that were far away, but nobody really thought about pointing them up toward the heavens until Galileo did. And Galileo pointed his telescope up to the heavens and he started seeing some rather unusual things. Now, again, Galileo was a proponent of the heliocentric theory, okay? And so some of the observations that he made actually did support that theory. One of the things he saw was Venus, and this is out of his notes here, and you see where he saw Venus and Venus, had phases like the moon, which it would have had anyway in the geocentric. But the main thing is that it changed size. And if Venus was orbiting the Earth, it wouldn't change size. And so this was really big deal. This obviously was a clear indication that it was not orbiting the Earth. It was probably orbiting the sun. Okay. And then he also made observations of Jupiter, and he noticed these little stars on either side of Jupiter that were seen to be moving from side to side and didn't ever leave, the proximity of Jupiter. So they weren't background stars. And he soon realized that these were moons that were orbiting Jupiter, which is a big deal because in the geocentric theory, everything orbited around the Earth, and so this was contrary to that. Now, he made a number of other observations, and eventually he published all of that in his pamphlet called The Starry Messenger. And he published all these observations in support of the heliocentric theory. For that, he was in fact brought before the Roman Inquisition, and he was given a sentence. He was placed under house arrest for the remainder of his life. But because of his observations and other observations, gradually the heliocentric theory was accepted, making the sun the center of the solar system and the universe. Just as a side note, it was only 390 years later, in October of 1992, that the church finally acknowledged that it had erred in condemning Galileo and exonerated him. Okay, so moving along. So now we have the sun as the center of the universe. And so we've displaced humanity by, the distance from the sun to the Earth, but that we still felt okay about that because at least the sun was at the center of the universe. And so humanity was still kind of at the center of the universe. Okay. But we still didn't know exactly, as telescopes came into being, it became, we came to realize that the stars are not all just on a celestial sphere. Okay, that they do have different distances. And so we still needed to try and figure out exactly, okay, what is the universe? Okay, how large is it? One of the first people to try and define that was William Herschel with his sister Caroline. Okay, now we know William Herschel, of course, is the discoverer of Uranus in 1781, but he also made a number of observations. He was a great observer. He cataloged a number of deep sky objects, and he also tried to define what he thought the shape of the universe was. Okay, and so he did star counts and plotting, and so he came up with what he felt was the shape of the universe in 1785. And so from star counts, he came up with this shape for the universe, and assumed, of course, that the solar system was at the center of all this, and that star clusters and nebula and galaxies, they were all part of the Milky Way. They were all part of this, the galaxy, which was the universe. Now, we talk about nebula, okay? And at that time, there were a lot of fuzzy things in the universe, okay? And we look at nebula ourselves, and nebula, of course, are clouds of gas and dust. But galaxies also kind of look like nebula as well, because their telescopes weren't large enough to really resolve any individual stars. And so we can see here on the right something that they called spiral nebula, because they had these spiral arms. They could see the spiral arms in their observations. And so we have, the regular nebula on the left here and the spiral nebula that were a special kind of nebula on the right. But nevertheless, they were all nebula, and they were all part of the Milky Way. Just if you wanted to know, the one on the left is called, it's actually two nebulae in there. One is called the North American Nebula on the left, and on the right is the Pelican Nebula. And the object on the right is NGC 718. It's in Pisces. The North American Nebula is in Cygnus. Okay.
Hey, Dave, let me just do a quick pause here.
Yeah.
On 20 minutes straight. I don't see any questions in the chat. Does anybody have any questions on anything so far?
This is a good pausing point here. So let's do that.
Does anybody have any questions for Dave?
I was just reading about non-inertial frames of reference. So if For these advanced listeners who want some entertainment, Google that and see what you find.
Advanced frames of reference. Okay.
Non-inertial frames of reference. That's when
No.
you're staying on the Earth looking up and you're thinking that you're in the center of everything.
Oh, okay. I see what you're saying.
Any other questions, guys? All right, Dave, back to you.
Okay, so chronologically, we're now moving up to around the turn of the century, around the year 1900. And at that time, a Dutch astronomer by the name of Jacobus Kapteyn again wanted to try and define what the universe looked like. And he took observations of stars from a number of astronomers and made plots. And of course, by this time, we also had the ability to do some calculations by parallax measurements. We had the capability of doing that by this time. And so we also were able to actually get some judging about how far away stars were. And so Kapteyn put together this view of the universe, Milky Way galaxy, if you would, and he defined it as a flattened stellar disk. Okay, and based on the data that he had, he figured it was about 30,000 light years in diameter and about 6,000 light years in thickness. And of course, the sun was near the center of this galaxy. Now, keep in mind that 30,000 light years was mind-boggling. It's a huge distance, you know, and so people, this is really, really big for folks to think about. And so this made a lot of sense to a lot of people. And so there was a concept that, you know, throughout the universe you'd always have stars. And so this whole idea that the Milky Way galaxy was in fact the extent of the universe sounded very, very good to a lot of people. Okay.
Dave, what years were you referring to here for Kapteyn?
This is around 1900. Okay. Around 1900, start of the century. Okay. And so this is what his view of the universe was. Okay. Now, around the same time, actually about 1912, something else, we need to talk about this as well, and that is the importance of Cepheid variable stars. Okay. They come into play here when we get into the debate. Okay. Now, 1912, a Harvard computer, gals who were hired by Edward Pickering to take a look at glass plates of stars and make estimations about their magnitude, their brightness, their size, their spectral signature, and all like. One of them was Henrietta Leavitt, and Henrietta Leavitt was tasked with documenting variable stars in the large and small Magellanic Clouds. And there are variable stars that are all over the sky. Okay, and they could be eclipsing variables, or they could just be varying on their own. But they usually have a pattern of variability, and one pattern was defined as a Cepheid variable because it's the initial star that was found with this was Delta Cepheid. Okay. And so when the pattern matched Delta Cepheid, it was considered a Cepheid variable star. And what Henrietta Leavitt found in her studies was that it appeared as though the magnitude or the brightness of the star, we're talking about the absolute magnitude, and I'm not going to go into a lot into absolute magnitude versus visual magnitude, except to say that visual magnitude is how bright the star appears to us here on the Earth. And absolute magnitude is how bright that star would be if it were at about 10 light years. Okay. And they use that relationship to plug into a formula called the distance modulus. And they can tell the distance to the star by taking the absolute magnitude and the visual magnitude and plugging it into this formula, find the distance to the star. Now, there's different ways of finding the absolute magnitude. Their spectrum, for instance, will give you some idea, but there is no real, I mean, to a certain extent, there's a little bit of interpretation in that. But what she found when she was doing her studies of Cepheid variables is that there was a relationship between the absolute magnitude of the star and the period of its variability. And this was huge because now you could actually check the variability of a Cepheid variable star and know what its luminosity was or its absolute magnitude and plug it into the formula and know how far away that star was. And Cepheid variables are pretty common. They're bright stars, so you can see them and not only in our own galaxy, but in other galaxies. But this was a key finding and a very important distance indicator that Henrietta Leavitt found out. And in fact, today it's actually known as Leavitt's law. So it's really is a big deal.
Hey, Dave, just a quick question. Do you know how they determined that period to absolute magnitude relationship? Like, how did they actually figure that out?
Well, she just noticed that the period and luminosities, there was a correlation to how bright they were, and then they used parallax for known stars that were Cepheid variables to check, okay, how bright it was versus the period, and correlate that, and found the relationship was accurate. So that's how they checked it.
Thanks.
Okay.
Does anybody else have any questions right now?
All right.
All right, all yours.
So let's go to the Great Debate. The Great Debate was held at the National Academy of Sciences meeting on April 26th. The meeting was from April 26th to the 29th in 1920. And it was regarding the nature of spiral nebula that were, with regards to the nature of spiral nebula, there were two camps of astronomers. Those who believed that the spiral nebula were part of the Milky Way and that the extent of the universe was in fact the Milky Way galaxy. And there were others who believed that spiral nebula were actually island universes that were outside of the Milky Way, much farther away. So George Hale, who was a revered astronomer at the time, the director of the Mount Wilson Observatory, proposed that we put a debate together at the National Academy of Sciences to consider arguments on both sides. Okay. You see here, this is obviously the program, and to the right is the program for Monday. And so I blew up a part of it, and there's 8:15 p.m. Is the discussion, the scale of the universe. Harlow Shapley and Heber Curtis were the two people who are going to argue about this. So the debate was actually called a discussion. Okay. It was actually not well publicized, and quite frankly, it wasn't well attended by astronomers. And it really didn't take the form of a debate as much as each man was given about 40 minutes to present their side of the argument. I think it's rather ironic that earlier that day, George Hale talked about the new 100-inch Hooker telescope at Mount Wilson Observatory, and we will find out that this telescope was instrumental in solving the discussion about the Great Debate.
Hey, Dave, we've got two quick comments.
Sure.
Mark Peterson mentioned that the Cepheid variables and the Magellanic Clouds were all at the same distance, so that
That's true.
you can compare the periods to the brightness.
Yes, that's true too. Absolutely.
And then Doug Plunkett mentioned that there's an article in Sky and Telescope last month about Leavitt and these calculations.
Yes. I was actually reading about that. So it's a good article. I highly recommend it. Okay. What else do we have here? Okay. So there's this. All right. So let's talk about the two sides of the debate and the men who represented them. On the left, here's Harlow Shapley. Now, he was a young, up-and-coming astronomer representing those astronomers who believed that the Milky Way galaxy was the extent of the universe, and every object we observe, including spiral nebula, were within the Milky Way galaxy. Representing the other group was the veteran astronomer Heber Curtis, who believed that spiral nebula were actually other island universes like the Milky Way, but much farther away, making the universe much larger. And so the debate brought up several other discoveries that would drastically alter our view of the universe and humanity's role in it. let's take a look at it now. So Harlow Shapley was the director of the Mount Wilson Solar Observatory at the time. Now, he wanted to gain directorship of the Harvard College Observatory, which was probably the premier observatory at the time. It was, of course, the Harvard Observatory that had all of the glass plates of photographs of the northern and southern hemispheric clouds that were being used to gather all this data about stars and the brightness and so on and so forth. He felt his performance at this debate was critical toward gaining the directorship of the Harvard College Observatory. Now, he had published articles in 1918 and 1919 in the Astrophysical Journal regarding globular clusters in the Milky Way galaxy. And in those articles, he based the asymmetrical distribution of globular clusters and estimated that most of the globular clusters are in one half of the sky. And he used the Cepheid variables to measure distances to as many of these globular clusters as he could, and surmised that the center of the Milky Way was toward that part of the sky. And he placed the center of the Milky Way at about 60,000 light years from the sun. Now, this meant that the diameter of the Milky Way was much, much larger than what Kapteyn had surmised. He felt that the Milky Way was about 300,000 light years in diameter, 10 times larger than what Kapteyn had said it was. And because of the size of the universe, the Milky Way was so large. I mean, we thought 30,000 light years was huge. 300,000 light years is even, much larger. Spiral nebula had to be located within it because it was so large. Further, a colleague of his, Adrian van Manen, was another astronomer at the Mount Wilson Observatory, and his job was to track the proper motion of stars. Okay, and one of the things he did was he said that he had looked at some of the spiral nebula and has claimed to successfully measure the internal rotational motion of several spiral nebula, including the Pinwheel Nebula. If these galaxies were outside the Milky Way, they would be too far away to measure that rotational motion. Okay, so that was his argument.
And Dave, how was they measuring that with Doppler?
No, proper motion. So he was actually able to see some movement. So he said. This is what he said. Okay, so just we'll get to that. Okay. Herschel Curtis was an astronomer at the Lick Observatory and very well respected. This is a veteran astronomer. Okay, he actually supported the Kapteyn model of the universe, shaped like a flat lens with the sun at the center. His arguments were much more focused on the subject of the debate, and that is the nature of the spiral nebula and the size of the universe. So in 1917, Herschel Curtis published a paper in which he observed that nova occurred in spiral nebula much more frequently than in the rest of the Milky Way galaxy. Okay, so you would expect that nova would be at a rate that would be consistent throughout the galaxy and not focused in a particular part of the galaxy. Okay, so this would imply the spiral nebula were quite distant and were island universes similar to the Milky Way. In addition, Curtis cited Vesto Slifer, an astronomer at the Lowell Observatory, who measured high radial velocities for spiral nebula. Okay, he did it through the spectrum. Okay, and their velocities would be much slower relative to the sun if they were in our own galaxy. Okay, now Curtis did not believe that Cepheid variables were good distance indicators. Again, 1920, this is only a few years after Henrietta Leavitt had published her findings. And he was one of the skeptics of it. And so he didn't think that Cepheid variables were good distance indicators. And so he felt that Shapley's measurements of globular cluster distances were suspect. He also did not believe that Van Manen's measurements of rotation, as they involved angular motions much smaller than had ever been measured and were unrealistically small to be measured. Okay, to your point, Matt, right? Okay, so we get to the end, and so who won the debate then? Well, let's be clear that this was more of a pair of presentations than a debate as such. But on the subject of the debate, Curtis was probably the winner. He was much more focused on the subject itself and presented the scientific evidence grounded in observation to support his argument. Both men presented arguments that challenged our view of the universe, though, and humanity's place in it. So let's review a little bit. Okay, so for Harlow Shapley, his correct points was that the sun is well away from the center of the Milky Way. And this is significant because if the sun was at the center of the universe, then the fact that it was 60,000 light years away from the center of the Milky Way galaxy, or the center of the universe, humanity is nowhere near the center of the universe then. And that's kind of a big deal, okay? Because that's, remember, for 1,500 years, that's what we believed, okay? Our galaxy is much larger than Kaplan had hypothesized, and he is correct. But it was probably, his estimate was a little too large. I think the current estimates are about 160,000 light years or thereabouts. And that Cepheid variables were in fact valuable distance indicators, and we have proven that to be true. Okay. His incorrect points are that spiral nebula are in the galaxy. Okay. He didn't even consider what distance the spiral nebula were, so he considered the side point of how large our galaxy was, and that didn't even play into his argument. He didn't take into consideration that interstellar dust is not a significant absorber of light. That's incorrect. It is, and it has to be taken as a factor in determining the size of the galaxy. We know that there's dust in the galaxy. We can't see the center of the galaxy because of the dust that's in between us and the center of the galaxy. And that his incorrect point was that the extent of the universe, of course, was in fact our galaxy. On the other side, we look at Herschel Curtis. Okay, his correct points were that he had solid arguments about why spiral nebula are external galaxies. Okay, he had valid scientific data. He had the count of the nova counts to talk about that. He was also correct about Van Maenen's measurements of spiral nebula rotation. They were incorrect. I don't know how he made them, but the instrumentation at the time, and of course we know now that those are actually galaxies that he was measuring, they were far too far away for him to be able to measure rotation, and he didn't have the instrumentation to do that. Okay. And the incorrect points, he didn't believe that Cepheid variables were good distance indicators, and he questioned Shapley's claim about the distance to globular clusters. But we know now that they are. Globular clusters are not as far away as Shapley had indicated. And we know that some of them are that far away. Most of them are within the 20,000 to 30,000 light year range, but still, they are pretty far away. And he was wrong about the size of our galaxy. Okay. He believed the captain's estimation was correct. He was wrong about the sun being at the center of the galaxy, and he too was wrong about interstellar dust not being a significant absorber of light. In the end, both men's arguments were compelling. Neither had produced conclusive proof either way. However, the debate was a catalyst for both men's careers. Shapley did go on to become the director of the Harvard College Observatory from 1921 to 1952, becoming one of the best known astronomers in history. Curtis became the director of the Allegheny Observatory in 1920, and then went on to become the director of the observatories at the University of Michigan, his alma mater, in 1930. So how was the argument resolved? Well, for that, we need to return back to the 100-inch telescope newly installed at the Mount Wilson Observatory. The Hooker 100-inch telescope was completed in 1917. It was named after John D. Hooker, who provided a substantial amount of funding for building the telescope. Now, just to give you some feel for this, 100 inches is about 2.5 meters, which at the time was the largest telescope and would remain the largest telescope in the world from 1917 to 1949. The newest telescopes in Chile are 30 meters in diameter. So we all know that professional astronomers also have aperture fever. Okay. One of the first astronomers to use this telescope was an astronomer by the name of Edwin Hubble. Okay. Here we have a picture. I love this picture of getting the mirror up to the top of Mount Wilson. Well, it looks like a really what could possibly go wrong with that, right? So, okay. So one of the things that Edwin Hubble was looking at was the Andromeda Nebula. And because of its size in the sky, it was one of the most studied nebula at the time. And so here we see Hubble guiding the Hooker 100-inch telescope in 1923. And then the camera would be taking pictures. There's a shot of the telescope itself, pretty impressive. All right. And so as Edwin Hubble was studying the plates of the images that were being made by the Hooker telescope, he was making some notes because you could see some individual stars there. And then he noticed that one of the stars was a Cepheid variable star. And so he was a proponent that the Cepheid variables were in fact a good distance indicator. And so he made the calculation and determined that the distance modulus revealed that this star was some 1.5 million light years away, well outside even the largest estimate of the Milky Way galaxy. Okay, so this was really conclusive proof of a galaxy outside of the Milky Way. And this began the hunt to determine what other galaxies were out there. Within a year, other nebula, like the Triangulum, were found to be other island universes. And we go on from there. So this is 1924. Obviously, from then until now, we've discovered that there are a lot of galaxies out there. This is the famous Hubble telescope deep field view. The objects to the bottom right that have the real colorful star spike, and at the top left, this colorful star spike, those are actual stars. Everything else you see in there is a galaxy. Every little dot is a galaxy. Okay.
Hey, Dave.
Yeah.
Mark Peterson mentioned that Hooker funded the mirror, and then Andrew Carnegie funded the rest.
Oh, yeah. It was part of the Carnegie telescopes. Yes, that's correct. Yep.
Does anybody have any questions since we have a pause here?
This is the end of my presentation. So, yeah.
Oh, there you go. Take it away, Dave.
So, today we know that the universe, of course, is much larger than we could have possibly imagined. And there are literally trillions of galaxies out there. But the Great Debate was kind of a catalyst toward gaining that kind of knowledge. Any questions?
Matt Dunham asked, what is a typical Cepheid variables period, or how many years do you have to watch it to be able to use it for distance?
I'm going to go back to that slide because there's a table in there. They're not very long, actually. So,
like days, isn't it?
It's days to here, right here. So see on the right here, the period is in days there. So we're only talking less than 50 days for even the longest period, and most of them are much shorter than that. So that's what makes them pretty nice, is that you don't need to wait a long time to determine what the period of the Cepheid variable is.
But the most important point of that table is that the longer the period,
the brighter
the luminosity.
Right, exactly. Yep.
Anybody have any other questions for Dave?
Well, I just have more of a conjecture for Dave. There's been a lot of discussion lately about dark matter and the fact that a lot of the universe is rotating faster than it should, and we're off by a factor of 10. So therefore, there must be a lot of dark matter out there that we can't observe, and they're looking for it. And,
Yep.
So when they find it, what's going to happen then? Do you think the universe is going to shrink by a factor of 10, maybe? That maybe instead of being 13 billion years since the Big Bang, maybe it will be only 1.3 billion years? Or, a factor of 10 is large, even for a scientist.
It is, and I have no doubt that we're going to make discoveries that are going to alter our present view of the universe, right? When you think about this, the Great Debate and what happened afterwards really drastically changed what our view of the universe was at that time. We imagined before the Great Debate and Hubble's discovery that we were the center of the universe, and the universe was the Milky Way galaxy. That was it, right? And so that all changed, All right. And I have no doubt that we're going to make discoveries in the future that could potentially drastically alter what we believe today about the universe, right? There's so much we don't know, right? And we base our knowledge today on what we know, but of course it's what we don't know that's going to change that, right?
Dave, let me add something to that. Since the discovery of Cepheid variables, there's since been other types of stars that can be used for these purposes as well as standard candles.
Absolutely.
Supernova, for example, or other types of variable stars. And the idea is that we have a pretty good idea out a few billion light years now. We have candles that can go out a few billion light years. So I don't know if it would shrink as he was asking about down to 1.3 billion years wide as the age of the universe, but it'd be something greater than that.
Yeah. So somewhere in between. And you can learn more about both of those from my book, The Stories of Astronomers and Their Stars, because I do talk about standard candles and I talk about Cepheid variable stars as well. So
Ron Schmidt asks, how did Shapley and Curtis respond to Hubble's results?
I didn't look into that. That's an interesting question. I think that Shapley probably had to have been okay with it because he believed that Cepheid variables were in fact valid distance indicators. Curtis Heber probably may have questioned it at first, right? But I got to believe that scientists will change their minds as well once they have more information.
Good deal. Anybody else have anything for Dave?
Yeah, this is Doug Plunkett. Can you hear me?
Yep.
Yeah, just kind of an interesting little point, and it's not really astronomy, it's more geology, but there's a very interesting book called The Earth's Deep History, which is an account of how our geology was so misinterpreted up until the mid 1800s because everything was based on what the Bible said.
Oh, right.
In fact, if you go up to William O'Brien State Park, there's actually a glacial erratic on the river there, by the river, with a sign that somewhat attributes it to Noah's flood.
Oh, yeah. Yep. Yeah, the church, as I mentioned before, the church not only was a political and religious authority, but they were also the scientific authority for a very long time. And so, and a lot of what the church believed had its basis in the Bible. And so they tended to skew, I guess, whatever discoveries were made based on what was in the Bible. So
yeah. We should also add here, Dave, that all of this is Western thought, right?
It is all Western thought. Absolutely. Yep.
Eastern philosophies, and even like the Maya, for example, some of these other cultures did have the sun as the center of the solar system, a long time ago.
Yeah.
And these kind of things. So
yeah, that's absolutely true. That's something I wanted to dive into a little bit more. Is unfortunately there's not a whole lot of material on it, but not only Mayan and Inca, which were very advanced societies on over this side of the world, but the Chinese as well, and they were very knowledgeable as well. So yeah.
Ron Schmidt asks, I don't know about changing his mind, as Planck said. A new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die.
Well, there's that too. Acceptance by attrition. I like it. Okay.
Yeah, both sides probably end up dying. All right. If there's nothing else for Dave, thank you so much.
You're welcome. It's been a pleasure.
Really excellent talk, and I think our crowd really liked it. We have 33 people on the call today.
Okay, good deal.
Pretty good number. Just want to make sure I remind everybody that the next talk is going to be on January 22nd, Saturday at 1 p.m. Jerry Jones will be presenting on Astronomical League programs for beginners, as well as observing techniques. If anybody has any further questions for Dave that they think they thought about after this talk, drop me a note in the forum and I'll be sure to forward it to Dave, or just respond to Dave directly.
Yep.
All right, guys. Thank you for your time and have a great rest of the weekend.